Hey everyone, I'm Arsha Niksa, and today I'll be talking about the theory of Euler's method. And hopefully in the next video we'll be covering the coding part and we'll try to solve a differential equation numerically. So as for today, we have two topics of discussion. The first one would be Euler's method. Note that in today's video we'll focus on the forward Euler method. And the second topic of discussion would be the 13th problem of IYPT 2020, the friction oscillator. So we'll basically go through its theory and its corresponding differential equation, and we'll try to rewrite it in a way that we could use Euler's method in order to numerically solve that differential equation. Alright, so let's start with an example. So basically, you have a pendulum. This is the y-axis. And you want to find its position, its vertical position, y, as a function of time. So you want to know what function is it that works with the pendulum. So let's say you release the pendulum from y0. And so the initial condition would be written in this way. And you have a differential equation corresponding to this pendulum. So it's something like this. And y0 is equal to y0 is equal to y0. Alright, so this is the problem. Now, the Euler method provides us with a way in order to solve this equation. Now, note that, let me just give let's say warning before going to the next part. Note that in Euler's method we are trying to discretely solve the differential equation. So it's basically an approximation to the result. So let's say this pendulum has a solution of, let me just write it down. So this is the y-axis, this is the t-axis, the time. And basically what we could do with Euler's method in a practical way, let's say, would be that we'll have points on the solution, and they're not necessarily on the solution. They have a little bit of error usually. So yeah, something like this. So this is a discrete solution. This is not something that provides us with a function, something that could be achieved using analytic methods. All right, so that was the warning. So let's move on to what the Euler method gives us. So the forward Euler method provides us with a method of solving this equation. How? This is how. So we have now this might look a little bit weird, but I'll try to break down what each part represents. So if you remember, we said that this method is a discrete method. So basically what happens is that instead of thinking of y as a function, we are thinking of it as a point, as a data point. So basically, for example, this would be y0, this would be y1. We're basically indexing y's, those points. y3, y4, y5, and so on. So this is a data point. And what is h? H is basically called the step size. The step size is the difference between two consecutive t's. So let me just go to another page and redraw the graph so that it wouldn't be so messy. So these were the points. So this is t0, y0. This is t1, y1. This is the t-axis. This is the y-axis as usual. This is t2, y2, and so on. And basically, h gives us the delta t, the difference between two consecutive t's. So let's say tn plus 1 minus tn. All right, so this is h. So let's go back to the previous page. So this was the equation. So we got this one. What about f? F is the function that we had from our differential equation. This is f. So basically, in Euler's method, you take the previous data point. So let's say you know the solution up to this point and you want to know where the next point is. So you want to find y3 at t3. So you want to know what y3 at t3 is, and you know the solution up to t2. So what you have to do is that you have to get it from the Euler's method the following way. So you say that y3 is equal to y2. We know what y2 is, plus h. H is something that you could arbitrarily decide. So we have this one too. F of y2 t2. Let me just change the order of that. t2 y2. So basically, you put t2 and y2 into the function f, multiply that by h, add y2 to it, and then you have y3. So now that you have t3 y3, you could ask yourself, okay, what about t4 y4? So, and you could just repeat this process and go on and on and on. So it's kind of an iterative process. You're constantly iterating in order to get to a certain point. So let's draw a diagram here. So basically, you have the initial condition, y0, and you have t's. So t's are like time. I don't know. At what t points do you want to know y? Those are the times. Like, let's say t0 is 0, t1 is 0.1 seconds, t2 is 0.2 seconds, and so on. So basically, tn is equal to n divided by 10 seconds. All right. So in order to find y1, you do that magic, so to speak, with y0, t1, and t0, and you get y1. When you get y1, you get y2. When you get y2, you get y3, and you get yn, and so on. And you could just end the process at whichever point you think is enough. Let's say we finish it at n, where n is equal to 100. So our simulation is taking 10 seconds. All right. So this is the process of solving a differential equation with Euler's method. Now let's go through an actual IYPT problem. So let's go to IYPT 2020, problem number 13. So this is the friction oscillator. So in this problem, we have a rod and two cylinders, and those cylinders are each, this one is turning clockwise, and this one is turning counterclockwise. And as a result of these rotations, you'd have a weird motion, a linear motion for the rod that is basically oscillating on top of. So now let's take a look at this paper, which goes in depth about the Timoshenko oscillator, which is another name for the friction oscillator. And if we take a look at this paper, we see that there's a differential equation. So for this problem, we have a differential equation. So this is x double dots. Dots usually represents derivatives. So this is the second derivative of x with respect to time, plus 2g mu k divided by Lx equals 0. So this is our equation. Let me write that down. All right. Okay. Now, this is the equation. So this is called a second order differential equation. It's a different territory, so to speak. Now, why is that? It's because x double dots, which was the second derivative of x with respect to t, is second order. It's like taking derivatives 2 times. So this is not, so because of this, we cannot easily write it down in the format of dx dt is equal to fxt. We have to pull up a trick in order to write it in this way. Now, what is that trick? So we basically get help from a helping variable. Now, let's do this. We'll call x dot, which is the first derivative of the first derivative of x with respect to t, v. This is our velocity, and this is our first equation, equation 1, and then we'll basically rewrite this equation using this one. So we would have v dot. This is because x double dot is v dot based on this definition. V dot plus 2g mu k divided by Lx is equal to 0. So now we have a system of two equations. Now let's rewrite these two in the familiar format of dx dt is equal to fxt, and for this one dv dt is equal to f of v and t. And next here. Alright, so to do this, for the first one, this is quite simple. This is already done. So we have dx dt is equal to v. Now, let me just change the name of this function. Let's call it g. So this is our f. So we have f of x and t. So it's not really it's kind of like it's not necessarily a function of that. fxt is equal to v. And for the second one, we have, let's drag this one here. We have v dot, or let me write it in the Leibniz notation, dv dt is equal to minus 2g mu k Lx. Now let's call this alpha for simplicity, so it would be equal to minus alpha x. So let's go to a new page. So as a result, we got two equations. The first one was dx dt is equal to v, and the second one was dv dt is equal to minus alpha x. Now, the initial position is something that you could give to your simulation, so to speak, and the initial velocity, v naught, is also something that you could arbitrarily define. So these are our differential equations, and now the rest is simple. You basically use Euler's method for each of them semi-independently. So for the first one, you would have xn plus 1 is equal to xn plus h, and note that this was called f, this was called g, plus hf xn tn. And for vn plus 1, you would have vn plus hf vn tn xn. Oh, I'm sorry, this is supposed to be g, so yeah, this is it. So you basically have to iteratively use these equations, and then you would get your result. So in the next video, we'll cover the coding part, so hopefully it would become a little bit more clear. So, but for now, this is it. These are the two equations that we've gotten to, and we have to use a programming language in order to iteratively solve for vn plus 1 and xn plus 1 and get our numerical results. This was for today's video. I hope you have a nice day, and goodbye.